Hi everyone. Today I have with me problem 4.40 from Young and Freedman's University Physics textbook, and that is from either version 14 or 15. And depending on which version you have, your problem number might be different than mine. Okay, so this is from the forces chapter, and yeah, let's get started on this problem. But before we go ahead and do that, please don't forget to like and subscribe and leave a comment if this video is useful or helpful to you, or if you find any of my other videos useful or helpful. And if you don't, then I'm sorry about that, and I hope that one of my future videos is helpful, but thank you so much for watching anyways. Okay, so two blocks connected by a light horizontal rope sit at rest on a horizontal frictionless surface. Block A has mass 15.0 kilograms, and block B has mass M. A constant horizontal force, F is equal to 60.0 newtons, is applied to block A. In the first 5.00 seconds after the force is applied, block A moves 18.0 meters to the right. A, while the blocks are moving, what is the tension T in the rope that connects the two blocks? B, what is the mass of block B? Okay, so first of all, if I stumble over my words, please excuse me, or if I cough, please excuse me. I've had a long day at work and I recorded this video like 5 times. I keep forgetting to add something, so I'm a little bit of a mess today, so excuse me in advance. But okay, let's get started on the actual problem. So let's go ahead and annotate the diagram that we have in the bottom right corner. It's really great that we have a diagram so we can visualize this problem a little bit better. But another thing we can do to make it even better is to actually just go ahead and write down the information that's in the question that applies to the diagram in the diagram, so that it's just a little bit more intuitive. So mass is equal to 15.0 kilograms. We see that block B has mass of M, right? So just M kilograms. And I'm actually just going to go ahead and erase this M over here just for sake of, I don't want to cause any confusion. And this force is 60.0 newtons. That's not 600, that is 60. Okay, and because we can't really fit, there's a lot of other numbers here, but we can't really fit those in the diagram because how are we going to really, write that? It takes 5 seconds. So let's actually go ahead and write down like a whole section of knowns. Okay. So knowns. So we know that block A has mass of 15.0 kilograms, and block B has mass of M kilograms. And a constant horizontal force is F is equal to 60.0 newtons. And in the first 5 seconds, that's going to be 5.00 seconds. So the time that it takes for in the first 5 seconds after the force is applied, block A moves 18 meters to the right. So the time that it takes is 5 seconds for it to move. And how far does it move in those 5 seconds? It moves 18 meters to the right. So I want to pull your attention to something. It says block A moves, right? But really, if there's tension in the string right over here, right? So if there's tension and there's tension, that means that the entire system is moving, right? Because you can't have tension in a string in this problem, right? And have block A move and block B is not moving. It's different if there's no tension in the string, right? So you can have, if there's no tension in the string, then block A is moving, but block B is, there's a limp string, so nothing's really pulling at box B or block B. Yeah, so there we have it. They both have to be moving for 5 seconds for 18.0 meters. All right, okay, so now there is another piece of information that's sort of hiding in this question. And if you've already found it, it's right here at the top, and it says 2 blocks are at rest. So we know that VI is 0 meters per second. So 2 blocks are at rest. Okay, so now what can we do? We have all of our knowns down in one place. Now, the interesting thing, well, this is not really actually interesting. This is more like an interesting thing about me, is that I used to hate doing these problems. I was terrified of them in high school. And then in university, sorry, I just burped. Okay, excuse me. So in university, I actually figured out a system, and every time I'd follow it, it would lead to, the right answer. So that actually eased my anxiety so much. So I'm going to show it to you, and then hopefully this will work for you. So the key is really to draw force body diagrams after you write down your notes. And you want to write down a force body diagram for every single system in your, every single subsystem in your system. Okay, so what do I mean by that? So let's write down FBD for our force body diagram, and or diagrams, because there's going to be more than one. And I'm writing it just to the right of this page right over here, just because I want us to be able to keep these diagrams up while we work on the question on the left side. So I'm just going to go ahead and define a little coordinate system. So let's go ahead and say that this is y and this is x. Let's also go ahead and say that this is positive x and this is minus x and this is positive y and this is minus y. Okay. Now, our first system is, let's assume that A and B are, or our first subsystem is actually the system itself. So let's say A and B, let's think of A and B as one system, right? And what are the forces that are working on this? So there's force of gravity, of course, right? And then there's going to be normal force. So normal force is really interesting. There's always so much confusion about this, but really, if there's a flat surface, normal force is going to be perpendicular to that flat surface. So Fn and Fg. There's also going to be this F right over here, this applied force. So that's F. Okay, so that is for our first diagram. I hope I'm recording. I am not going to do this again if I'm not. Okay. Yes, I'm recording. Good. Okay. So, oh no. Okay, let's go back. Sorry about that. That was a problem I never ended up doing. Okay. So that's our first system, or first subsystem. The second subsystem, you might guess, is A. So let's just talk about A by itself and what are the forces that are on A. Again, we have Fg and we have Fn, right? Because we're on a flat surface. And we have this F that's applied. And then we actually have this Ft. We have this tension force. All right, so those are all the forces that are on A. Now, what about B? Because that's the last system, right? We have Fg, Fn, and then we have our Ft, right? Because here on B, tension is going to be this way, but on A, tension is going to be this way, right? Okay, so that makes sense. But let's go ahead and simplify these diagrams just because it's not really, we've written everything down, but not everything's really relevant to our problem. And as you might have guessed, it's actually the fact that we don't need any information in the y direction for this question specifically. And the reason is because we know that these blocks aren't jumping up and down, right? They're not floating. There's no motion in y. And so if there's no motion in the y direction, then that means Fn and Fg cancel out. And if the forces were not equal to each other, then there would be some motion in y, right? So let's go ahead and just cancel out y. So all we really have is for, I'm going to go ahead and circle this in yellow. For a problem, not problem, but for system A and B, we just have this force. For A, we just have F and Ft, and then for B, we just have Ft, right? So let's go ahead and actually, you know what I'm going to do? I'm going to do you one even better. I'm going to go ahead and I'm going to erase all the y, just so that you can even better visualize what are the forces that we're actually just focused on. And that's just the x direction. Okay, there we go. So those are our three diagrams. And I'm just going to go ahead and label them as 1, 2, and 3. And okay, so now what we can do is we can actually go ahead and write down all of our relevant equations or create equations out of these subsystems or diagrams. That's better. Let's create equations out of these diagrams. So equations for our first one, it's going to be, okay, so for our first one, our equation for A plus B, all of our forces are really just, our force is equal to mass of A plus B times the acceleration of, the system. And actually, I should just go ahead and say that acceleration of the system is equal to acceleration of A is equal to acceleration of B, right? Because this rope is taut. Okay, so that is equation number 1, because we know that force is equal to mass times acceleration. Now for 2, we know that the forces that are on A, it's going to be F, right? Because this is the positive side, this is the negative. It's going to be F minus Ft, and that is equal to the mass of A times the acceleration of the system. And then for 3, it's going to be all the forces that are on B, that's just Ft, right? And that means that Ft is mass of B times the acceleration of the system. Awesome. Okay, so there we have it. Those are all of our equations. Now, what do we really want from this question? Let's go back to the problem. A, while the blocks are moving, what is the tension in the rope that connects the 2 blocks? So we're looking for tension. We're looking for tension like this. Yeah, we're looking for tension. And we have 2 equations that can actually give us that, right? But we want to use the one that we already have information in our knowns, right? Or else what's the point? If we have 2 unknowns and 1 known, there's not really much we can do. But if we have all knowns and 1 unknown, then we can solve for the unknown. Okay, so now let's go ahead and just look at 2. We can't use 1, right? Because 1 doesn't have Ft, so that's not going to give us the information we want. So in 2, yeah, we have this. We said it's 60, right? Ft, we're trying to figure this out. And then for mass, we have that right over here, right? We have that right over here. So, and then acceleration of system. So we don't have that explicitly, but interestingly enough, we have 3 pieces of information that we can use to get acceleration, right? So that's from our kinematics chapter. So we can use our kinematic equations to help us find what the acceleration is, right? Okay, so it seems like we can use equation 2. Let's look ahead at equation 3 just for the sake of seeing if there's more than one way to do this problem. So, yep, this is what we're looking for. We do not have mass of B, right? So we're actually looking for mass of B in part B. So no, we can't use equation 3, but we can use equation 2. So let's go ahead and do that to find the tension. So what is the tension? So problem A, the tension is going to be, so let's go ahead and rearrange this equation so that we can get, so we can isolate for tension. So it's going to be Ft is equal to F minus ma times system, or acceleration of the system. And that way we can isolate for Ft and solve for Ft. Okay, so we have F, which is 60, minus mass of A, which is 15, times acceleration of the system. So acceleration of the system, how do we get that? Well, remember we said that we have these 3 pieces of information that can help us. Let's go ahead and use our kinematic equation to solve for the acceleration. So it's going to be F, well, okay, so D is equal to V naught T plus half of AT squared right? Because we have d, we have t, we have vi, so this is a perfect equation for us. And we're looking for acceleration. So let's go ahead and use this equation to isolate for a. So right off the bat, we can actually go ahead and cancel this because v naught is 0. So d is equal to half of at squared. If we want a, it's going to be 2d divided by t squared. I think, let me just double check that. 2 times d divided by t squared. Okay, yeah, that's right. And I'm going to plug in all of my values. So its acceleration is equal to 2 times 18 divided by 25, right? And the acceleration that I get is 1.44 meters per second squared. And let me just double check that on my calculator just because I don't want to make any mistakes. Okay, so yeah, 1.44 meters per second squared. So this is going to be 1.44 meters per second squared. And Ft is going to be 60 minus 15 times 1.44. And that is equal to 38.4 newtons, right? So that is what our tension is. It's going to be 38.4 newtons for, that's what Ft is, the tension in the rope right over here. Okay, awesome. So we solved part A. Now what about part B? What is the mass of block B? So there's really two ways to go about this, and I'm actually going to go about it the more difficult way just because you can always use parts of your answer that you acquired in the question to help you solve for more for other parts of the question, right? But if you think about it, let's say this is a test or this is some sort of evaluation. What if you made a mistake in one of the previous parts, right? You don't want to carry that mistake over. That's why you should always go back and use all the original information that you possibly can. If you don't have a choice, then that's different, but you always want to try to use the original pieces of information. And so I'm going to go ahead and do this a little bit more complexly. That's not a word, so I'm going to do this in a way that's a little bit more complex. Well, not really complex. I would just say it's more thorough. Okay, so part B. We want to find out what is mass of block B. Okay, so we could go ahead and use this right here, right? But again, we just solve for Ft, and we don't really want to use piece of information that we got from part A because what if I didn't make a mistake here right now? But if this were a test, let's try to figure out a different way to do this. So let's pretend this is a test. Okay, so another thing is that, yeah, okay, so let's pretend this is a test. So we want to find out MB. MB, let's go back to our equations and see which ones have MB. So this one, but we said we don't really want to use this. We can also use this right over here, right? Because we have the acceleration of the system, which we solved for. We have our force, and we have mass of A. So if we go ahead and rewrite this, it's going to be force and mass of A plus mass of B and multiplied by the system. And we want to isolate for mass of B. Okay, so let's go ahead and isolate this just in the equation first. So it's going to be F divided by A system, right, minus MA is going to be equal to MB. And the force is going to be 60, right? So that's the force of the system. And the acceleration of the system was 1.44 meters per second squared. And minus the mass of A is going to be 15 kilograms, right? Yeah, 15 kilograms. So that means that MB is it's going to be 26.67 kilograms. So that's MB. And let's just double check with our equation number 3, just because if this is a test, that'd be a great way to check our answer. So FT, we said is, so double checking, FT, we said was 38.4, and we said that the acceleration of the system is 1.44. And so what is going to be MB? 38.4 divided by 1.44 is equal to 26.67 kilograms. So perfect. That is our final solution. And that's the answer to part B. So I hope that was helpful. If you have any questions, please feel free to leave them in the comments or send me an email. And if this was helpful, please don't forget to like and subscribe and share with your friends or classmates or whoever you share YouTube videos with. And thank you so much for watching. See you next time.